Number 7.
Yeah. So FTC function values. Right here. And number 7, you said?
Yes, please.
Okay, so number 7, it says a pizza heated to a temperature of 350 degrees is taken out and placed in a 75-degree room at a time t equals 0 minutes. The temperature of the pizza is changing at a rate of negative 110 e to the negative 0.4 T degrees Fahrenheit per minute. To the nearest degree, what is the temperature of the pizza at time t equals 5? Okay, so if like, let's say T of T, let's say this is the temperature of the pizza at time t. Okay, say that's the function. This quantity that they're giving us right here is really T prime of T, right? So according to FTC, I know that the temperature of the pizza at 5 minutes is going to equal the temperature of the pizza at 0 minutes plus the integral from 0 to 5 of T prime T. Does that make sense why that's true? Because if I were to write this another way, this could be written as the integral from 0 to 5 of T prime is really T of 5 minus T of 0, right? That's FTC part 1. This is FTC part 1. This is also FTC part 1. All I did is I just took this T of 0 and moved it to the other side of the equation. That's it. So this is what you would do. The initial temperature they're giving us is 350 degrees. So this is just going to, I'm going backwards here, but this is just going to equal 350 degrees plus the integral from 0 to 5 of this function here, which is really just the rate of change of the temperature. So it's negative 110 e to the negative 0.4 t dt. And use your calculator for that. Okay, so this is, remember on your calculator, it's math 9. So you do math 9. Actually, hang on a second, I need to do the 350. So it's 350 plus math 9, the integral from 0 to 5. What I'm integrating is that derivative function, which is negative 110 e to the negative 0.4 t. So this is negative 110 times e to the negative 0.4 x and dx. So that's it. The final temperature is 112.212. Remember, whenever you use your calculator, round everything to the nearest 3 places. If you wrote 112.2, it would be, you would get points off on the AP test. That's the worst reason to get points off. You understand all the calculus. Oh, it does? Unless it says to the nearest degree. Then do it to the nearest degree. 112. Thank you. Yep.
So one of the questions said, like, identify the direction that the particles are moving. Direction is, I don't know if it was like, it was positive value, and I don't know if it was up or to the right.
What number is it?
It's 1A on more FTC.
It's possible I wasn't clear. Definitely possible it is. 1A.
Or B, sorry.
Particle moves along a line so that its position, yeah, I wasn't really clear, huh? I guess I was thinking that it's horizontal, but whatever. Yeah, so as long as you understand, velocity is positive, then the direction of movement is right or up. They'll make it more clear on the actual question. Other questions? Yeah, John?
9 on FTC function values.
Okay. Number 9 on FTC function values. So this says a particle moves along the x-axis so that its time, at any time 0, its velocity is given by this function. It says the position of the particle is 3 at time 0. What's the position of the particle when its velocity is first equal to 0? So the first thing we need to do is figure out when its velocity is first equal to 0, so that we know like the ending time that we're looking at. So we could just set this velocity function equal to 0. We could set cosine of 2 minus t squared equal to 0. Okay. Now how to solve that? There's a couple different ways you could do it. You could do it like an analytical way, or you could do it using a calculator. I'll try and do it in an analytical way first. So first of all, cosine. I know that the graph of just cosine by itself looks like this, right? The first time that that equals 0 would be when the angle that you're looking at is pi over 2, right? 90 degrees. So when this right here is pi over 2, that's going to be the first time that t equals 0. I mean, sorry, that velocity equals 0. Does that make sense? So just solve that equation now. 2 minus t squared equals pi over 2. Does that make sense? And then solve for t. So here I have t squared equals 2 minus pi over 2. And t is equal to the square root of 2 minus pi over 2. And we're looking at time, so it can't really be negative. And let's just verify, like if I actually do this graphically on my graphing calculator, if I take the cosine of 2 minus t squared, make sure my calculator is in radians, it is, and then just graph it. I'm just going to do like zoom. Actually, yeah, zoom. Why not? Trig. See what happens. All right. So let me see. I want to figure out the first time that it equals 0. So that would be that point right there. So second calc, find the 0, and left bound, right bound. Yes. Remember, you're allowed to solve equations using your calculator, and that's what I'm doing. I'm solving an equation using my calculator. So 0.655, if I do this, if I take the square root of 2 minus pi over 2, oh, it's the same. It's the same. So I did it analytically. I did it using my calculator. I got the same answer. That's a good thing. So it's 0.655, or I could use this as my limit of integration, either one. Okay, so now back to the problem. If I'm trying to find the position of the particle at that moment, that's like S of 0.655, which is equal to the initial position, S of 0, plus the integral from 0 to 0.655 of v of t. This is just like that problem we just did, right? This is FTC part 1, just written a different way. So now you just do that on your calculator. Okay, so it's going to be the position of the particle is 3 at 0. So it's going to be 3 plus at 9, the integral from 0 to, now I don't have to retype this over again. I don't think I can just do answer, previous results. I don't have to round it too soon. And then the velocity function, which is cosine of 2 minus t squared. T. Okay. So that's the answer, 2.816. Does that make sense? I thought the hard part of this problem was really finding the t value that you're using for the upper limit of integration. That was the hard part of that problem. What else?
11D.
Same handout. 11D. Let me erase this. D. Okay.
Yeah.
Sorry? Yeah, sure. The rate at which rainwater flows into a drain pipe is modeled by this function. So it's a rate. This is a derivative, right? The pipe is partially blocked, allowing water to drain out the other end at a rate model. This is also a derivative. Okay. There are 30 cubic feet in the water in the pipe at time t. Okay. So first, how many cubic feet of rainwater flow into the pipe? So remember the definite integral of a rate is really total change in that quantity. So if I'm trying to find the amount of rainwater that flow in, I just need to take the definite integral of the rate at which the water flows in over that time interval. Does that make sense? Like if I take the integral from 0 to 8 of r of t, dt, right? That's going to give me the amount of water that has flowed in. If I took the definite integral from 0 to 8 of d of t, that's going to give me the amount of water that flows out during that time. Does that make sense to everybody? So now, this is all the work you have to show, and then just give an answer. You don't have to show anything else if this was a free response question. So let's, in a question like this, my strategy is always to enter in the functions they give you really carefully one time and then never type them again. You'll save time that way. So this is 20 times the sine of x squared divided by 35. I'm going to enter that into y1 rather. Y1. And then into y2, I'm going to enter d of t. So it's negative 0.04 e squared, or cubed, plus, minus, plus 0.4 t squared, plus 1.96 t. There's that whole derivative. And then just double check it, make sure you didn't make any mistakes. Okay, so for part A, all I need to do is from my normal working screen, I just need to take math 9, definite integral from 0 to 8 of y1, because that's what I typed in r of t as. So we do variables, y variables, function 1, dx. And that's the answer, 76.570. So this is 76.570 gallons. That's literally all you would have to do, and you would get full credit for part A. This is an actual free response question, by the way, that I just put on this handout. Okay, part B says, is the amount of water in the pipe increasing or decreasing at time t equals 3? How can you tell? Yeah, figure out the rate at which it's flowing in and figure out the rate at which it's flowing out. If it's flowing in faster than it's flowing out, then of course the amount of water is increasing, right? If it's flowing out faster, then the amount of water is decreasing. Again, I can do this all on my calculator with showing very little work and get full credit. So all I would need to do here for part B, put it here first. Part B is just find R of 3 and D of 3. And then just compare them, see which one's bigger. So you can do this completely on your calculator. All you have to do is from the main working screen, I'm gonna graph the two functions. I'm gonna do window, I'm gonna graph them on the domain that they give us, which is from 0 to 8. So I'm gonna graph this from 0 to 8. And then I'm going to do zoom fit. So there's the rate at which it's flowing in, the rate at which it's flowing out. And then to find the values of these functions, just do second calc value at x equals 3. So this is y1 of 3, which is r of 3. So it's 5.086. Gallons per hour. And to get to the other function, you just press the down arrow. That function will change to the second function. So it's 5.4 gallons per hour. So you can see, since the water is flowing out faster than the water is flowing in, that means that the amount of water in the pipe is decreasing. So since D of 3 is greater than R of 3, the amount of water is decreasing. That's it. Okay? Part C, at what time is the amount of water in the pipe at a minimum? Well, look at the picture. If you look at this picture, for a little while, the R function is less than the D function, right? This part, the R is below the D. But once you get over to here, the R is above the D, right? So what that means is water's flowing out faster than it's coming in on this section of the graph. And on this section of the graph, water's flowing in faster than it's going out. So if the amount of water in the pipe is decreasing, right at that moment when they're equal, when the functions cross, the rates are equal, that's when the water's at a minimum, because from that point on, the water starts increasing again. Does that make sense? I think it intersects more than once, does it? I can't. There's part of the graph that's blocked by the thing. Yeah, it doesn't look like it. It doesn't look like they intersect more than once. So all you need to do is just determine that spot right there where they intersect. Does that seem logical? Does that make sense? I mean, you could do this like just by making a new function. Like you could say like, you could do this. I don't know if this is a wise thing to do, but here's what you could do. You could say that the amount of water in the pipe at time t is really just equal to the initial amount of water in the pipe, right, which they tell you is 30 cubic feet, plus the integral from 0 to t of the rate at which the amount of water in the pipe is changing, which is really just R of t minus D of t. Does that seem logical? Because if you take any rate, right, any derivative function, and you integrate it and do a definite integral, right, that gives you the total amount of change of that quantity, right? So do you agree that R of t minus D of t is the rate at which the water level is changing at any moment? It's the rate at which water is flowing in minus the rate at which water is flowing out. That seems logical, right? So if I definitely integrate that over any time period, it gives me the amount of water that changes over that time period. So if I just take the initial amount plus the amount it changes from 0 to t, that's going to give me the amount at any moment. So if I'm trying to find this function, forget about what this function actually is. If I'm trying to find out when this function is at a minimum, do the first derivative test. I take the derivative and I do a little sign chart to figure out when it's increasing and decreasing, whatever, right? So I'm going to do that. A prime, the derivative of 30 is 0. The derivative of this is FDC part 2, right? You're taking a definite integral from 0 to t, and you're differentiating it. Well, what do you get? You're going to get R of t minus D of t. This is the rate at which the water is changing. Well, when is this equal to 0? This is equal to 0 when R of t equals D of t. When the rate at which water is flowing in and the rate at which water is flowing out are equal to each other. Okay? So then if I find that point of intersection on my graph, which I will in a second, it's going to be here somewhere or whatever. I mean, you can tell just from the shape of the picture that this is decreasing, increasing. Because on this interval, D is bigger. And on this interval, R is bigger. Does that make sense? I just need to find that point now. So I go to my calculator, second calc, intersect, first curve, second curve, guess, boom, there it is. 3.271 hours, or 272. 3.272 hours. And that's what the question's asking. At what time is the amount of water in the pipe at a minimum? Justify your answer, because for all t values less than that, D of t is greater than R of t, which means that A prime is negative. And for every time value that's greater than that, R of t is better than D of t, which means A prime is positive. So that's the point at which A prime changes from negative to positive, which is what a minimum is. Okay? And then D. All right, so for part D, it says the pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow into and out of the pipe at the given rate since the pipe begins to overflow. Right? But do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. So here, this is the amount of water in the pipe. Just set this equal to 50. And that will give you the amount of time that it'll take before the pipe begins to overflow. If you could solve it somehow. Everybody understand that? Or equivalently, I could have forgotten about the 30 and just said, let's find out when the total amount of change is equal to 20. Because if we know we start at 30, then it has to fill up 20 gallons before it overflows. So I don't know how clear this is, but that would be my answer for part D right there. D. Okay. Any other questions on that? That one? That was a tricky one. It's kind of a lot to it. All right, what else? Yeah.
On the second handout, more FTC.
Uh-huh.
Give me your numbers.
Yeah. More FTC. More FTC number 6. I have to erase this again. I think it's stupid that this writing doesn't stay where it should be. Like that would be an easy thing to fix if I'm working for Smart Word Technologies or whatever it is. But hey, can't do everything. All right, number 6. The rate at which raw sewage enters a treatment tank is given by this equation. So this is, again, a rate. It's a derivative, right? Treated sewage is removed from the tank at a constant rate of 645 gallons per hour. So this is the same type of problem. We have water or sewage coming in, sewage going out. The treatment tank is empty at time t. At what rate is the sewage entering the tank when t equals 3? You just substitute 3 in here. This is the rate at which it enters the tank at any moment in time. So for part A, it would just be E of 3. And again, I would do the same thing I would always do here, which would be to enter this in as R1 on my calculator, and then I don't have to worry about it again. Okay, so it's equals, I'm going to clear the 2 functions that I had from the previous problem. So this is 850 plus 715 sine 850 plus 715 cosine pi t squared over 9. So pi x squared divided by 9. Okay, so there's E of t. So then I would just do second calc value at 3. And it's 135. It's not on my picture because I didn't have a good window, but I could change the window to go from 0 to 4 and make sure you can see it and everything. Like if I went from 0 to 4 and then zoom fit, there's the function. So second calc value at 3, so it's 135. This is 35 gallons per hour. Gallons per hour. Okay, and that's all the work you would need to show for that. Part B, how many gallons of sewage enter the tank during the time interval from 0 to 4? This is the rate at which the sewage enters the tank. So the number of gallons that enter the tank would be the definite integral of this from 0 to 4. That's it. This would be definite integral from 0 to 4 of E of t. And that's all the work you have to show for that. Okay, they expect you to use the name of the function. You don't have to like write this all out on your paper after that. Okay, so on here, again, I can do it from this screen, or I can do it from the main working screen. I could just from here, I could say second calc, definite integral is choice 7 from 0 to 4, and it'll do it for me. Now, if you notice it's shading, now you hopefully realize why it's shading, because this represents the area of that shaded region. It's the area between the curve and the x-axis. Remember we talked about that last week. So this is the answer. It's 3981.023. Gallons. And then part C, how many gallons of sewage are in the tank at 3 hours? You take the initial amount, which I tell you is 0, but you take the initial amount plus the amount that entered minus the amount that left, right? So if this is the total of number of gallons that, different time. So sorry, I can't use my result from part B because this is saying t equals 3. This one said t equals 4. So I can't use that. But it's the same concept, right? The number of gallons in general is going to be the number of gallons at the start, which it says is empty, plus the definite integral from 0 to 3 of E of t. That's the amount that enter the tank in the first 3 hours, minus the amount that leave the tank in the first 3 hours. Well, it's saying it's a constant rate of 645 gallons per hour. So this would just be 645 times 3. That's the number of gallons that left during those 3 hours. That's it. So on my calculator, I could go to the main working screen. I could say math 9, integral from 0 to 3, variables, y variables, function 1, dx, minus 645 times 3. So that's it. That's how many gallons are in the tank at t equals 3. 1417.193. That makes sense? I mean, the most important key idea that you need to understand of all this stuff is the definite integral of a rate is the amount of change of whatever that rate was of the quantity of. Okay, so if you have a rate that represents the rate at which anything, literally, like runners are crossing the finish line, right? Then the definite integral from 0 to 8 would be the total number of runners that cross the finish line. You have a rate derivative It's definite integral, it's just the total change of quantity. It's like the accumulated change. Okay, what else? Yeah.
Could we quickly go over on FTC function values?
Sure. Number 8. All right, number 8. A particle moves along the x-axis so that at time t, its acceleration is given by this function. Velocity of particle is 2 at time 1, and find the velocity of the particle at time 2. So would you agree that A is really B prime? Okay, so if you're trying to find the velocity at 2, it's just the velocity at 1 plus the integral from 1 to 2 of B prime, which is it. That's it.
I think I tried to do it without a calculator, so like,
Oh,
it was like ln
Yeah, we can't do
1
that.
plus 2 to the t, so I'm like, well, how do I?
yeah, no, we haven't learned how to do that.
Yeah.
But yeah, this is just totally use your calculator and that's the answer. You want me to do it? You good? Okay. What other questions? Yeah.
Do 10D on the same.
Yeah. D. Right, but do not solve an equation involving an integral expression of R, whose solution gives the earliest time t at which there is no longer a line for the ride. All right, let me read the question. There's 700 people in line for a popular amusement park ride. The ride begins to operate. Once it begins operation, the ride accepts passengers in the park, closes 8 hours later. While there's a line, people move onto the ride at 800 people per hour. This graph shows the rate at which people arrive at the ride. Okay. So just practically, just logistically, you know that if you look at, if this is the rate at which people are arriving at the ride, and we know that people are leaving the ride via getting on the ride and taking it at 800 people per hour, doesn't it make sense that the moment at which there's no line is when the total number of people, wait. What if the rates are equal? Okay, so if the rates are equal, okay, that's when the line is decreasing. Hang on a second. Earliest time at which there's no longer a line for the ride. Okay, so if we wanted to calculate the number of people in line, right? There's 700 people to start with. So the number of people in line, let's just say that that's like A of t. The number of people in line at any moment t is the initial number in line, which we know is 700, plus the integral from 0 to t of the rate at which people arrive at the line, r of t, minus the rate at which people leave the line. Let's just say that's like d of t or whatever, dt. Do you agree that this is really the total number of people in line at any moment? So if I want this to be 0, I just need to know what these things are. So this is really 700 plus the integral from 0 to t, r of t. I'm going to separate these up into 2 separate integrals. And the rate at which people are departing the graph is 800 people per hour, right? So that's 800 t. Minus, thanks. Minus. So if I want to know when this is equal to 0, just set it equal to 0, and that's it. That's an equation that involves an integral
Pardon
expression
the
of r.
interruption. Would the person student that owns a red GMC pickup truck, license plate number KGL 8587. Please move your truck as per the custodian staff. Thank you.
Does that make sense though? So if I just set this equal to 0, that's exactly what they're looking for. They're looking for an integral expression that involves R that if you were to be able to solve it, it would give you the time in which it's no longer a line. Okay? What else? All right. I have one problem here. What do you think? The answer is 3/4. Okay, so remember the way that you analyze limit as x goes to infinity is you look at the order of the top and the order of the bottom, generally, right? Well, the order of the top here is really 2. Even though it's a 4, you're square rooting that whole thing, so it's really 2. The order of the bottom is also 2. If the orders are equal, then you have to look at the fraction of leading coefficients, right? If you look at the fraction of leading coefficients, this coefficient is 3 and this coefficient is 4, which is why it's 3/4. Now, you have to be careful in some problems like this. There was one like this in the math quote handout that I gave out that it ended up being different depending on whether you're going to infinity or to negative infinity. And the reason why that one was different is because that one could have been positive in some situations or it could have been negative. I think it turned out that this exponent was an odd number. So it could possibly have been, like if this was a 6 and this was a 3, then this answer would be either 3/4 if you're going to positive infinity, or negative 3/4 if you're going to negative infinity. Well, in this case, it just says x goes to positive infinity. So we know the answer is 3/4 anyway. Does that make sense? But you have to be careful in certain problems like this, because sometimes it depends whether you're going to positive infinity or negative infinity, whether the answer is positive or negative. So just be careful about problems like that. That's why I wanted to give you that one. All right, so if you haven't handed in any of those handouts, make sure you do so, please. Because otherwise, they just go as zeros. And, you know, you don't want zeros on homework.
Oh my God, I have that shirt.